There is an object 10.5 billion light-years from Earth that breaks virtually every model we have for how the universe is supposed to work. It is not a theoretical object. It is not a candidate or a hypothesis. It has been photographed, measured, and confirmed by multiple independent research teams over several decades. And the more precisely we measure it, the worse the problem gets. The object is called TON 618. It is the largest confirmed black hole in the known universe. And the reason it matters is not its size, it is when it formed. To understand why TON 618 is such a profound problem for physics, you first need to understand what a black hole actually is, because the popular image most people carry around is significantly wrong. A black hole is not a cosmic drain. It does not reach across space and pull things toward it. The gravitational field of a black hole behaves exactly like the gravitational field of any other object with the same mass. If you were to replace our Sun this instant with a black hole of identical mass, Earth's orbit would not change at all. The planets would continue their usual paths. Nothing would spiral inward. We would all eventually freeze to death in the darkness, yes, but from a gravitational standpoint, the solar system would carry on as though nothing had happened. What makes a black hole different from a star or a planet is not the strength of its gravity at a distance. It is what happens when you get too close to the center. All that mass is concentrated into an extraordinarily small region. As you approach the center, the gravitational gradient across your body becomes so steep that the force pulling on your feet is enormously stronger than the force pulling on your head. You stretch. You compress sideways. Physicists call this spaghettification, which is technically accurate and genuinely unsettling to think about. More relevant to the story of TON 618 is the event horizon. This is the boundary around a black hole, where the escape velocity, the speed you would need to travel to escape the gravitational pull, equals the speed of light. Inside that boundary, nothing moves fast enough to get out. Not spacecraft, not particles, not light itself. The event horizon is not a physical surface. There is nothing there you could touch or feel. It is a mathematical line in space, beyond which the future only points inward. Cross the event horizon, and every path through space-time curves downward toward the singularity at the center. You have not hit a wall. You have entered a region of space where getting to the center is not just likely, it is geometrically inevitable. Time itself bends in ways that make escape impossible regardless of how much energy you apply. Most black holes fall into two broad mass categories. Stellar mass black holes form when a massive star exhausts its nuclear fuel and its core collapses under its own gravity. These objects range from roughly 5 to perhaps a few dozen times the mass of our Sun. They are scattered throughout galaxies, occasionally revealed when they pull gas from a companion star or when two of them merge and produce ripples in space-time that we detect with gravitational wave observatories. Then there are supermassive black holes. These sit at the centers of galaxies and are in a completely different weight class. The one at the center of our own Milky Way, known as Sagittarius A star, has a mass of roughly 4 million times the mass of our Sun. That sounds enormous. Compared to what is about to follow, it is almost quaint. TON 618 was first noticed in 1957 during a wide-field photographic survey conducted at the Tonantzintla Observatory in Mexico. The object was cataloged as entry number 618 on that survey's list, which is where the name comes from. Tonantzintla 618. Nobody paid it much attention. It appeared in the photographs as a faint blue point source, indistinguishable at a glance from tens of thousands of ordinary stars. That misidentification held for about 15 years. By the early 1970s, advances in spectroscopy allowed astronomers to break the light from that faint blue dot into its component wavelengths and read what those wavelengths were telling them. The story they told was extraordinary. The light was not coming from a star. The emission lines in the spectrum were characteristic of a quasar. Quasar is short for quasi-stellar object, a term coined in the 1960s when astronomers first started finding point sources of light that were far too bright and far too distant to be stars. What a quasar actually is the violently energetic core of a galaxy whose central supermassive black hole is actively consuming enormous quantities of matter. When gas and dust and the stripped-apart remains of stars spiral into a supermassive black hole, They do not fall straight in. They form a flattened, rotating structure called an accretion disk. Friction within the disk heats the material to temperatures of millions of degrees. The disk glows. It radiates not just visible light, but ultraviolet radiation, X-rays, and gamma rays in quantities that can outshine the combined output of every star in the host galaxy by factors of hundreds or thousands. A quasar, in other words, is a black hole eating, and eating so rapidly that the glow of its meal lights up a corner of the universe. This was already remarkable. But quasars were not new by the early 1970s. What made TON 618 stand out came when astronomers measured the precise redshift of its light. Light from distant objects is stretched by the expansion of the universe. The farther an object is, the longer its light has been traveling, and the more that light has been stretched toward the red end of the spectrum. By measuring how much TON 618's light had been redshifted, astronomers could calculate both its distance and the age of the universe when that light was emitted. The numbers that came back were staggering. The light reaching our telescopes from TON 618 left its source when the universe was less than 4 billion years old. Given that the universe is approximately 13.8 billion years old today, that means we are looking at light that has been traveling for roughly 10.5 billion years. The object we see in our telescopes is not TON 618 as it exists now. It is TON 618 as it existed in the deep past, in a cosmos so young it had barely begun to build the large-scale structure we see today. And the object producing that light was, by every measurement we could apply to it, completely unreasonable. Let us be precise about the scale, because numbers in astronomy are easy to let slide past without really registering. Our Sun contains approximately 2 × 10⁻30 kilograms of mass. That number is large enough that most humans cannot hold it in their heads in any meaningful way. So instead of kilograms, astronomers use the solar mass as a unit. Everything is measured relative to the mass of our Sun. Sagittarius A star, the black hole at the center of the Milky Way, has a mass of roughly 4 million solar masses, 4 million suns compressed into one object. TON 618 has a mass of approximately 66 billion solar masses. Some recent measurements and modeling revisions place the figure closer to 40 billion. The uncertainty itself covers a range wider than the total mass of Sagittarius A star by a factor of thousands. Either number 40 billion or 66 billion puts TON 618 in a category that required astronomers to invent a new name. They call objects in this range ultramassive black holes. There is no more extreme category above it because nothing larger has been confirmed. 66 billion solar masses. Every star you can see on a clear night, every star in every constellation, the entire luminous band of the Milky Way that stretches across the sky from horizon to horizon on a dark night away from city lights, all of it combined, does not come close to the mass of this single object. Our galaxy contains somewhere between 100 billion and 400 billion stars. Most of those stars are smaller than our Sun. Even if you added up the mass of every star in the Milky Way and poured it all into one point, you would still be well short of the mass of TON 618. The physical size follows from the mass. The radius of a black hole's event horizon, called the Schwarzschild radius, scales linearly with mass. Double the mass, and you double the event horizon radius. The event horizon of TON 618 has a radius of approximately 1,300 astronomical units. 1 astronomical unit is the average distance between Earth and the Sunday, roughly 150 million kilometers, or about 93 million miles. That distance, the one between you and the nearest star, is the unit. Now multiply it by 1,300. Pluto, the farthest major body in our solar system, orbits at an average distance of about 40 astronomical units from the Sunday. The event horizon of TON 618 extends more than 30 times farther than Pluto's orbit in every direction from its center. From edge to edge, through the middle, the event horizon spans roughly 2,600 astronomical units. If you set our solar system down at one edge of that boundary, you would need to line up more than 30 complete solar systems end to end, from the Sun out to Pluto and back to the Sun again, to cross from one side to the other. And you would still be inside the event horizon? Light itself, Traveling at approximately 300,000 kilometers per second, the fastest speed anything in the universe can move, would take roughly 2 weeks to travel from one side of TON 618's event horizon to the other. 2 weeks of uninterrupted travel at the speed of light, just to cross a single hole in space. The numbers become difficult to relate to human experience at this point because nothing in human experience has prepared us for them. The largest thing most people will ever directly perceive is perhaps a mountain range or an ocean. The largest thing most people can mentally scale up to with effort might be the Earth, or possibly the distance to the Moon. The distance from the Earth to the Sun requires genuine imagination for most people to hold. TON 618's event horizon contains 1,300 of those distances, in every direction from a single point. Imagine what the experience of being near such an object would be like. Not inside the event horizon, where the physics becomes even stranger, but at a safe observing distance near the edges of the accretion disk. First, the light. The accretion disk around a black hole of this mass would stretch outward for distances measured in light weeks in every direction. It would not look like anything you could compare to human experience. The innermost regions of the disk, where material spirals closest to the event horizon before being lost, reach temperatures of millions of degrees. That superheated plasma radiates primarily in X-rays and ultraviolet light. The outer regions of the disk are somewhat cooler, glowing in visible wavelengths, but the sheer size and luminosity of the structure means the total output of light and radiation would be incomprehensible. The estimated luminosity of TON 618 is roughly 140 trillion times the luminosity of our Sun. 140 trillion. Take the entire Milky Way galaxy, every single one of its hundreds of billions of stars radiating simultaneously, and place it next to TON 618. The quasar outshines the galaxy by a factor of several thousand. Then there is what gravity does to the geometry of space in that environment. The mathematics of general relativity, which has been confirmed by experimental evidence with extraordinary precision, predicts that an object as massive as TON 618 would warp space-time so severely in its vicinity that the usual rules of geometry stop applying. Time would run slower near the event horizon than it does in open space. If you could hover at some fixed distance near the outer edges of the event horizon, which would require an extraordinary amount of energy to sustain, a clock in your hands would tick more slowly than a clock in deep space, far from any mass. Drift closer, and the time dilation increases. At some point near the event horizon, a minute of your time would correspond to years, then centuries, for anyone observing from far away. Light from distant objects would be bent around the black hole, creating multiple images of the same source. The entire observable universe would appear wrapped and distorted into rings around the dark circle of the event horizon. The event horizon itself would be a perfect circle of nothing. Not black in the way a dark room is black. The absence of all photons. Not a surface you can focus on. Not a shape your visual system can find edges on. Just a region where the visible universe simply stops. Stars wandering too close to TON 618 would not fall in as solid objects. Long before reaching the event horizon, the tidal forces across the star's diameter would exceed the self-gravity holding the star together. The star would be torn apart. Astronomers call this a tidal disruption event. The stellar material forms a long streamer of gas that spirals into the accretion disk, eventually heating and contributing to the quasar's output. We have observed tidal disruption events around smaller supermassive black holes on dozens of occasions. At the scale of TON 618, entire dense star clusters could be consumed over the span of a human lifetime without any detectable change in the quasar's overall activity. But the physical scale and the extreme behavior of TON 618, while genuinely staggering, are not actually the deepest problem the object presents. The deepest problem is chronological. TON 618, as we observe it, existed when the universe was less than 4 billion years old. It already had 66 billion solar masses at that point. How did it get that big, that fast? To understand why this is such a thorny problem, you need to understand how black holes grow under normal physical rules. A black hole grows primarily in two ways. It can consume matter, drawing in gas and dust, and the disrupted material of passing stars. And it can merge with other black holes. For the matter consumption process, there is a physical limit on how fast a black hole can eat. As a black hole accretes material, the infalling matter heats up and radiates. That radiation exerts pressure outward on the surrounding material. If a black hole tries to eat too fast, the outward radiation pressure exceeds the inward gravitational pull and blows the incoming material away, temporarily halting accretion. The maximum rate at which a black hole can sustain accretion is called the Eddington limit, named for the British astronomer Arthur Eddington, who first worked out the relationship in the early 20th century. A black hole accreting at the Eddington limit doubles its mass roughly every few tens of millions of years. That sounds fast, but it is not fast enough. Start with a stellar mass black hole of about 10 solar masses at the beginning of the universe. Let it accrete continuously at the Eddington limit, never exceeding the maximum physical rate, never being shut down by lack of fuel. Run the calculation forward through the entire age of the universe, and you end up with a black hole of perhaps a few billion solar masses. Possibly. But TON 618 had 66 billion solar masses when the universe was less than 4 billion years old. That is not a gap that can be bridged by standard accretion starting from a small seed black hole. So how did it form? Astronomers currently have 3 main hypotheses, and none of them are fully satisfying. The first is called direct collapse. In the early universe, before the first stars had formed in large numbers, giant clouds of primordial hydrogen gas filled the cosmos. Under normal circumstances, these clouds would fragment into smaller pieces as they cooled and began to collapse, each fragment eventually forming a star. But in certain special environments, particularly regions where intense radiation from nearby sources prevented the gas from cooling and fragmenting, these massive clouds might have been able to collapse more or less directly into black holes without passing through a stellar phase at all. Direct collapse black holes would not start at a few solar masses. They would potentially form with masses of 10,000 to 100,000 solar masses or more. Starting from that much larger seed mass changes the growth calculation dramatically. From a starting point of 100,000 solar masses, sustained Eddington limited accretion over the available time could plausibly reach the observed mass of TON 618. The problem with direct collapse is that we have no confirmed observational evidence that these objects exist. The conditions required for direct collapse to occur are theoretically possible but specific and narrow. Whether they were common enough in the early universe to explain the population of ultramassive black holes we observe is unclear. The second hypothesis involves runaway mergers. In the dense environments at the cores of the first galaxies, massive young stars might have collided with each other before they had time to evolve normally. These stellar collisions would have created an extremely massive star, perhaps thousands of times the mass of our Sun, which would then have collapsed into a large black hole seed far more massive than anything formed from an ordinary stellar collapse. If these large seeds then merged with each other rapidly in the chaotic, collision-dense early galactic cores, the cumulative mass could have grown to enormous values in a relatively short time. The third hypothesis is the most radical and in some ways the most fascinating. Some cosmologists have proposed that primordial black holes formed in the first fractions of a second after the Big Bang. In the earliest moments of the universe, before the first atomic nuclei had formed, the cosmos was an extraordinarily hot and dense plasma of fundamental particles. Small-scale density fluctuations in that plasma could, in principle, have resulted in regions collapsing into black holes directly. Not from stellar collapse, not from gas clouds, but from the raw density of the newborn universe itself. If primordial black holes formed in this way, they would have been present from the very beginning of cosmic history. They would have been feeding and growing for the entire age of the universe. By the time the first stars formed and began producing quasar-style accretion, these primordial seeds might already have had enough mass to grow rapidly to the observed extremes. Primordial black holes are also a candidate for some portion of the dark matter in the universe, a possibility that adds further theoretical motivation for taking them seriously. But the evidence for their existence remains indirect and contested. None of these 3 scenarios is proven. All of them face observational or theoretical challenges. And the core fact remains: we have no complete, fully consistent model of how TON 618 reached its observed mass in the available time. The object is not just large, it is a standing challenge to our understanding of how matter organizes itself in the universe. The James Webb Space Telescope, which began science operations in 2022 and has since been delivering observations of unprecedented depth and resolution, has made this problem significantly more urgent. Webb was designed partly to observe the first galaxies and the first massive black holes in the early universe, at times and distances previously beyond the reach of any instrument. What it found has surprised even the astronomers who built and operated it. Scattered throughout the high redshift universe, at times when the cosmos was only a few 100 million to a few billion years old, Webb has detected a population of compact, reddish objects that have come to be called by some observers little red dots. These objects appear to be active galactic nuclei, meaning they are powered by accretion onto supermassive black holes. And many of them already have black hole masses of millions to billions of solar masses at ages when the universe had barely had time to form its first generation of stars. The existence of these objects makes the growth problem worse, not better. Each new detection at high redshift is another data point demonstrating that the universe was building massive black holes faster than our models predict. TON 618 is not an anomaly. It is the most extreme example of a phenomenon that appears to have been common. The current state of the field is that the standard model of black hole formation and growth, the one that has been refined and elaborated over several decades, does not adequately explain what we observe. Something in the physics of the early universe was different from what we assumed. Perhaps the conditions for direct collapse black holes were more widespread than we thought. Perhaps there is some accretion mechanism that can temporarily exceed the Eddington limit. Perhaps primordial black holes are real and numerous. Perhaps the answer involves some combination of all three, or something else entirely that has not yet been proposed. This is not a minor adjustment to existing theory. This is a fundamental gap. Now let us return to the question that has been implicit since the beginning. Is TON 618 doing anything to us? Is the light arriving from it dangerous? Is the object itself a threat? The answer on the threat side is straightforwardly no. TON 618 is 10.5 billion light-years away. The gravitational influence of any mass falls off with the square of the distance. At that distance, the gravitational effect of TON 618 on Earth is effectively zero, far below anything measurable. The object exerts less gravitational influence on our solar system than the nearest other star, and the nearest other star exerts essentially no influence on our day-to-day physics. The quasar itself, when active, produces jets of high-energy particles and radiation that stream outward along its rotation axis. These relativistic jets are among the most energetic phenomena in the universe, but they are highly directional. They fan out and dilute with distance, and even if one were aimed directly at Earth, at 10.5 billion light-years, the flux would be undetectable at our surface. The expansion of the universe is also carrying TON 618 away from us. The universe is expanding everywhere, in every direction, and at the distances we are talking about, the recession velocity exceeds the speed of light. That is not a violation of relativity. Nothing is moving through space faster than light. Rather, the space between us and TON 618 is expanding so rapidly that the distance measured between the 2 points is increasing faster than light could traverse it. This means TON 618 is not approaching us. It is receding at enormous speed into an ever-expanding universe. What is reaching us from TON 618 is only light, ancient, exhausted, red-shifted photons that left their source when the universe was less than 4 billion years old. Traveling through 10.5 billion years of expanding space, the vast majority of those photons have been scattered, absorbed, or lost to the void. Only an infinitesimally small fraction complete the journey. Those that do arrive already stretch to wavelengths longer than visible light, shifted into the radio and infrared portions of the spectrum by the expansion of the universe itself. But they do arrive. Tonight, as they have every night for as long as astronomers have been pointing instruments at that patch of sky, a trickle of photons from TON 618 is completing its journey and entering the mirrors and detectors of telescopes around the world. They are not dangerous. They carry no harmful energy. They carry information. Information about a time before Earth existed, before the sun formed from a cloud of gas and dust enriched by generations of dead stars. Before any of the atoms currently composing your body had been assembled into anything recognizable. photons that were emitted when the universe had not yet finished its first 4 billion years and have been crossing the void ever since. There is something genuinely worth sitting with in that fact. The light currently arriving from TON 618 is not old in the way that old light is described casually. It is not like looking at the sun 8 minutes in the past, or at the nearest star 4 years in the past. The light from TON 618 shows us a universe that no longer exists in any form accessible to us. The atoms in the accretion disk when that light was emitted have long since vanished into the event horizon or dispersed across the galaxy surrounding the black hole. The galaxy itself has aged by 10.5 billion years. Stars have formed and died in it. The quasar phase, that extraordinary feeding frenzy, has probably ended. Supermassive black holes do not feed continuously. They cycle through active phases when they have access to infalling matter and quiet phases when the supply runs low. What TON 618 looks like right now, in the actual present moment of the universe, is something we will never know. The light showing us TON 618 as it is today will not arrive on Earth for another 10.5 billion years. None of the entities currently inhabiting this planet will be here to see it. In some deep sense, the real TON 618 is permanently inaccessible to us. The one we can observe is a historical record, a photograph frozen in the deep past, a signal from a universe that no longer resembles the one we inhabit. Since the early 1970s, when the true nature of TON 618 was first recognized, the object has been studied with increasing precision, using a range of telescopic instruments and detection methods. Early optical and radio observations established the basic parameters: its distance, its approximate luminosity, the width of its emission lines. Later, more sophisticated spectral analysis refined the mass estimate using a technique called reverberation mapping. Reverberation mapping works by measuring the time delay between variations in the brightness of the quasar's central engine and corresponding variations in the emission from gas clouds that surround it. The gas clouds respond to changes in the central illuminating source, but with a delay proportional to their distance from the black hole. By measuring that time delay and the velocity of the gas, astronomers can calculate the mass of the central object with surprising precision. For TON 618, this method, combined with analysis of the width of specific spectral emission lines, yields the estimate of tens of billions of solar masses. There is genuine uncertainty in these measurements. Black hole mass estimation at cosmological distances is not as precise as measuring the mass of, say, a body in our solar system using Kepler's laws and direct observation. The error bars on TON 618's mass are substantial. The range of estimates from different studies and methods spans from roughly 40 billion to over 66 billion solar masses, which is itself a range wider than the mass of Sagittarius A star by an enormous factor. But even at the low end of the estimated range, TON 618 remains the most massive confirmed black hole in the known universe, and the uncertainty does not soften the growth problem. Whether we use 40 billion or 66 billion solar masses as the target, the chronological challenge is the same. The mass is too large for the available time under any conventional growth model. One of the important things Webb has enabled is a direct, high-resolution look at the environments of high-redshift supermassive black holes in much greater detail than was previously possible. The galaxy hosting TON 618 itself is not well resolved at its enormous distance. We see the quasar as a point source, surrounded by a faint extended halo of light from the surrounding stellar population. The galaxy appears to be large and actively star-forming, as might be expected from a system with so much gas and so much ongoing activity. The relationship between a supermassive black hole and its host galaxy has been a major area of research for the past few decades. It turns out that the mass of a supermassive black hole at the center of a galaxy is tightly correlated with properties of the galaxy's stellar bulge, particularly the velocity dispersion of stars in the bulge. Galaxies with large, fast-moving stellar populations tend to harbor more massive central black holes, and vice versa. This correlation has been measured across many galaxies at many distances. Its existence suggests that the growth of a galaxy's central black hole and the growth of the galaxy itself are not independent processes. They regulate each other through a feedback loop. When the central black hole is actively accreting and producing a bright quasar, the radiation and jets from that quasar can heat and disperse the gas in the surrounding galaxy, suppressing star formation. When accretion decreases, star formation can resume. This back and forth maintains the ratio of black hole mass to galaxy mass across cosmic time. Understanding exactly how this feedback works at the extreme scales represented by TON 618 requires observations that push the limits of current instruments. Webb is helping, but the answers are not yet in. Let us also consider what TON 618 tells us about the ultimate fate of objects like it. A supermassive black hole that exhausts its fuel supply, that has consumed the available infalling matter and dispersed the gas that fed it, will eventually settle into a quiet state. The quasar phase ends. The accretion disk cools and fades. What remains is a massive but inactive black hole sitting at the center of its host galaxy, still warping space and time around it, still holding everything nearby in its gravitational grip, but no longer producing the extraordinary luminosity of the active phase. The Milky Way's Sagittarius A star is in this quiet phase right now. It is not entirely dormant. Occasionally a gas cloud or a group of stars passes too close and briefly reignites a modest flare of activity. But compared to the roaring quasar phase, Sagittarius A star is essentially asleep. The same fate almost certainly awaits TON 618 if it has not already arrived. Given that we observe the quasar as it was 10.5 billion years ago, in the real present moment of the universe, the feeding that powered that extraordinary luminosity has very likely slowed considerably or stopped. The black hole remains, but it sits in the darkness of its galaxy, no longer advertising its presence with the unimaginable beacon of an active accretion disk. In billions of years from now, assuming anything survives that long, the black holes at the centers of galaxies will be among the last durable structures in the universe. Stars will eventually exhaust their fuel and die. Galaxies will merge, and eventually their stellar populations will fade. The protons making up ordinary matter may eventually decay, but a black hole, mathematically speaking, can persist for extraordinary spans of time. There is a mechanism by which black holes very slowly lose mass. It was proposed by the British physicist Stephen Hawking in 1974 and is known as Hawking radiation. The mechanism involves quantum effects near the event horizon that result in a very slow thermal emission of energy from the black hole. For a stellar mass black hole, this process operates at a rate so slow as to be effectively unobservable and would take longer than the current age of the universe many times over to have any measurable effect. For TON 618, with its incomparably larger mass, the Hawking temperature is even colder and the evaporation timescale even longer. A rough estimate of the time required for a black hole with the mass of TON 618 to evaporate via Hawking radiation is on the order of 10 to the 100th power years. That number is so fantastically beyond any human timescale that it is essentially meaningless to try to visualize. The universe as we know it would be unrecognizably different. The stars long dead, the galaxies dissolved, before even a tiny fraction of TON 618's mass was lost to Hawking radiation. TON 618 will outlast almost everything. It will sit in the dark for intervals of time that make the current age of the universe look like a fraction of a second, slowly radiating, slowly shrinking, until at some almost incomprehensibly remote future moment, it completes its evaporation. Even that endpoint is speculative. The physics of Hawking radiation in the final stages of black hole evaporation is one of the deepest unsolved problems in theoretical physics, involving unresolved tensions between quantum mechanics and general relativity that are known collectively as the black hole information paradox. The information paradox arises from a conflict between two well-established frameworks. General relativity, Einstein's theory of gravity, suggests that information about the matter that falls into a black hole is permanently lost when the black hole evaporates. Quantum mechanics, which governs the behavior of particles at small scales, holds as one of its fundamental principles that information cannot be destroyed. When a black hole evaporates completely via Hawking radiation, which framework wins? Does the information escape encoded in subtle correlations in the emitted radiation, as some proposals suggest, or is it truly lost, requiring a modification of one or both theories? The debate has engaged some of the most capable theoretical physicists alive for decades without resolution. TON 618, by virtue of its enormous mass, is an extreme test case for these ideas, though one that cannot be probed with any technology we can foresee. The questions it raises about information preservation will not be answered by observation of TON 618 specifically. They will be answered, if they are ever answered, through theoretical physics and possibly through observations of smaller, younger black holes in less extreme circumstances. What we can observe of TON 618 has already changed the field in several concrete ways. It has pushed theorists to take seriously hypotheses like direct collapse and primordial black holes that were previously considered exotic. It has helped motivate the development of more sensitive instruments capable of probing the high redshift universe. It has contributed to a growing body of evidence suggesting that the standard timeline of cosmic structure formation is systematically wrong in ways that we do not yet fully understand. The James Webb Space Telescope has only deepened this picture. Webb began its science mission in 2022 and almost immediately started producing results that exceeded expectations. Among the most striking early findings was a population of galaxies at extreme distances that appeared to have far more mass, far more stellar content than the standard model of galaxy formation predicted should exist at those early cosmic epochs. Some of these galaxies appeared to be as massive and as old-looking as galaxies we see in the local universe, yet they existed when the universe was only a few 100 million years old. They had somehow assembled enormous stellar populations in a fraction of the time our models allow. The discovery generated significant discussion about whether the standard model of cosmology, the Lambda CDM model, that has been the workhorse framework for understanding the universe's large-scale structure and evolution, requires modification. The black holes associated with these early galaxies only added to the problem. If the galaxies themselves were older and more massive than expected, and if those galaxies harbor supermassive black holes, as virtually all large galaxies do, then those black holes also needed to have formed and grown faster than theory predicts. TON 618 was discovered before any of this new data existed. Its challenge to standard models was recognized decades ago. The Webb findings have elevated that challenge from an interesting puzzle about one extreme object to a systematic discrepancy between theory and observation that affects our understanding of the entire early universe. We are in an interesting historical moment in cosmology. The instruments exist to probe the distant universe with unprecedented precision. The data being collected is rich and detailed, and a growing number of observations do not match the predictions of the best models we have. This is, from a scientific standpoint, an exciting situation. Discrepancies between theory and observation are where new understanding comes from. Every major advance in physics in the past century arose from taking seriously some measurement that did not fit the expected answer. The history of the specific problems TON 618 represents goes back at least as far as the 1960s and 70s, when quasars were first recognized as a class and their enormous distances were established. Early quasar surveys already found objects at high redshifts, with luminosities implying massive central black holes. The growth problem, the question of how such massive objects form so quickly, has been recognized in some form for more than half a century. What has changed is the quality and quantity of the data. Early estimates of quasar distances and luminosities were rough. The techniques for measuring black hole masses were primitive. The picture was impressionistic. Modern observations have sharpened the picture dramatically. We now have mass estimates for TON 618 precise enough to make detailed quantitative comparisons with theoretical models, and those comparisons are not favorable to the models. The survey landscape is also changing. The early astronomical surveys that produced the Tonnant-Centla catalog, where TON 618 was first logged, were photographic and shallow by modern standards. They covered large areas of sky but detected only the brightest objects. Modern wide-field surveys using digital detectors and sophisticated software can detect objects orders of magnitude fainter. They are finding quasars and high redshift supermassive black holes in numbers that were impossible to anticipate from the early survey data. The Sloan Digital Sky Survey, which ran its main survey phase through the 1990s and 2000s, cataloged tens of thousands of quasars at various distances. It found objects at very high redshifts that contributed to the evidence base for the growth problem. The Dark Energy Survey, the Hypersuprime CAM Survey in Japan, the upcoming Vera C. Rubin Observatory, and eventually the Nancy Grace Roman Space Telescope will push this inventory further. Each new survey finds more objects. Each new confirmed ultramassive or supermassive black hole at extreme redshift is another instance of the same problem TON 618 represents. The universe built these things, and the universe built them faster than our theories cleanly allow. One direction that theorists have explored is whether the Eddington limit itself is routinely exceeded in the early universe. Under normal conditions, as described earlier, the outward radiation pressure limits how fast a black hole can accrete. But this limit applies most cleanly to spherically symmetric accretion. Real accretion is not spherically symmetric. It occurs in an accretion disk, and the geometry of the disk changes how the radiation couples to the infalling material. In certain configurations, particularly in what are called slim accretion disks, where the accretion rate is very high, the radiation is trapped within the inflowing material rather than pushing it outward. In this regime, the effective accretion rate can substantially exceed the standard Eddington limit. This process, known as super-Eddington accretion, has been proposed as one possible mechanism for the rapid early growth of supermassive black holes. Super-Eddington accretion faces its own challenges. The physical conditions required to sustain it are demanding. The observational signatures of super-Eddington accreting quasars are being actively searched for. Some candidate objects have been proposed. But whether super-Eddington accretion was common enough in the early universe to explain the observed population of massive black holes is still under investigation. Another avenue is the possibility that the first stars, the so-called population 3 stars that formed from primordial gas before the interstellar medium was enriched with elements heavier than helium, were systematically more massive than stars forming today. Stars form from gas that can cool and fragment. The cooling mechanism in primordial gas, which contained essentially no metals, was less efficient than in enriched gas. This may have allowed gas clumps to grow to larger masses before fragmenting, potentially resulting in stars of thousands or tens of thousands of solar masses. These hypothetical massive first stars would have lived extremely short lives by stellar standards, millions of years rather than billions, and would have left behind massive black hole remnants. If those remnants had access to abundant gas and merged with each other in dense early galaxies, they could have seeded rapid black hole growth in the early universe. The challenge is that we have not yet observed population 3 stars directly. They formed so early and were so short-lived that detecting them requires observational capabilities we do not quite have yet. Webb has come closer than any previous instrument to the epoch when population 3 stars should have existed, and future observations may yet provide direct evidence of them or their signatures in the chemical composition of early galaxies. What we can say with confidence is this: TON 618 and the growing population of similar extreme objects are forcing a genuine reassessment of our models for early cosmic structure. The reassessment is ongoing. It does not have a clear resolution yet. The scientists working on these questions are not at a dead end. They have multiple hypotheses to test, multiple observations to make, multiple theoretical tools to deploy. But none of the current answers is fully satisfying, and the data being produced by instruments like Webb keeps raising the bar. There is also a philosophical dimension to what TON 618 represents, though the physics is interesting enough without embellishment. We are creatures who evolved on a single small planet, orbiting an ordinary star in a galaxy that contains hundreds of billions of similar stars. Our intuitions, our evolutionary heritage, and even our mathematical tools were all developed in reference to scales and energies and timescales that bear no meaningful relationship to the objects being discussed here. When we talk about 66 billion solar masses concentrated in a single region, or about light traveling for 10.5 billion years, or about an event horizon spanning thousands of times the diameter of our entire solar system, we are talking about things that no human sensory or intuitive apparatus can grasp directly. The fact that we can grasp them at all, imperfectly, through mathematics and measurement and careful reasoning, is itself remarkable. The fact that we have built instruments sensitive enough to detect the ancient light from TON 618 and extract from it information about the mass and age and behavior of the object producing it is a genuine achievement of science. And the fact that what we have extracted challenges our existing understanding is precisely what science is supposed to do. the greatest discoveries in the history of physics did not confirm what was expected. They revealed something strange. TON 618 is strange. The problem of how it formed is real and unresolved. The broader challenge it represents to our understanding of early cosmic history is being taken seriously by researchers at the leading institutions in the world. The investigation is ongoing. If you want to follow how this field evolves, the research is happening at a rapid pace. The James Webb Space Telescope is releasing data on a continuous basis, and new discoveries about high redshift galaxies and black holes are appearing in the scientific literature regularly. The preprint server RxEve, where physicists and astronomers post their research before formal publication, is a useful resource for tracking developments in real time. The things we do not know about TON 618 are in some ways as interesting as the things we do know. We do not know its current state. We do not know how its host galaxy looks today. We do not know whether the quasar phase has ended or is still continuing, because the light showing us the current state of the object will not arrive for another 10.5 billion years. We do not know definitively how it formed so quickly. We do not know whether there are larger objects still undetected in our surveys. We do not know the full population of ultramassive black holes in the observable universe, or what that population implies about the early history of cosmic structure. Every photon from TON 618 that reaches a telescope today carries information from a universe that no longer exists in any form we can access. Those photons have been traveling through expanding space since before Earth formed. They contain encoded within them the story of an extreme object in an extreme epoch of cosmic history. We are still learning to read that story correctly. The universe is larger than we thought, older than it needed to be for the structures we observe, and capable of producing objects that strain our best theories. TON 618 is not the end of that story. It is somewhere near the beginning of our understanding of it. The next large confirmed black hole, the next Webb discovery, the next unexpected result from a high redshift survey will add another chapter, and the chapter after that. The investigation continues. If that kind of question, how the universe builds its most extreme structures, and what those structures tell us about the fundamental rules of physics, is the kind of thing that keeps you curious, then consider subscribing and following along as new discoveries come in. The pace of discovery right now is genuinely extraordinary, and there is much more to come. The light from TON 618 is arriving right now, quietly, carrying ancient information, asking questions we do not yet know how to answer. That combination of fact and mystery, grounded completely in real physics and real observation, is what makes it one of the most extraordinary objects in the known universe. To truly appreciate the significance of TON 618, it helps to trace the history of how our understanding of black holes developed, because that history reveals just how far our thinking has had to stretch to accommodate objects at this scale. The concept of an object with gravity so strong that light could not escape dates back to the 18th century. In 1783, the English clergyman and natural philosopher John Michell proposed the idea of what he called dark stars, objects so compact and massive that the escape velocity from their surface would exceed the speed of light. Given the physics of the time, this was a remarkably prescient idea, though the mathematical framework to fully develop it did not yet exist. The framework came with Einstein. In 1915, Einstein published his general theory of relativity, which replaced the Newtonian picture of gravity as a force acting across space with a geometric description in which mass curves space-time itself and objects follow the straightest possible paths through that curved geometry. Within months, the German physicist Karl Schwarzschild solved Einstein's field equations for the case of a spherically symmetric mass and derived what is now called the Schwarzschild solution. This solution contains a critical radius, now called the Schwarzschild radius, inside which the escape velocity exceeds the speed of light, exactly as Michell had imagined more than a century earlier. For decades, physicists debated whether the Schwarzschild solution described anything physically real or was merely a mathematical curiosity. The prevailing view for much of the early and middle 20th century was that no real physical object would ever be compact enough to fit within its own Schwarzschild radius. Stellar evolution models suggested that dead stars would settle into stable configurations as white dwarfs or neutron stars, rather than collapsing without limit. That view was challenged and ultimately overturned through a combination of theoretical work and observational discovery. In the 1930s, the Indian-American physicist Subramanian Chandrasekhar showed that white dwarfs had a maximum mass beyond which they could not be supported against gravitational collapse. If a white dwarf exceeded what became known as the Chandrasekhar limit, it would collapse further. Work by Robert Oppenheimer and George Volkoff in 1939 extended this analysis to neutron stars and found that they too had a maximum mass. Above that limit, nothing could halt the collapse. The phrase black hole itself was coined by the American physicist John Archibald Wheeler in 1967, though Wheeler attributed the phrase to an unnamed attendee at a conference rather than inventing it himself. The term caught on immediately because it captured the essential physics so vividly. An object from which nothing escapes. A hole in the observable universe. The observational confirmation of black holes took longer and arrived from unexpected directions. Quasars, discovered in the early 1960s, were immediately recognized as implying enormous energy outputs from extremely compact regions. The scale of energy production required by quasar luminosities was so extreme that accretion onto a massive compact object, what we now call a supermassive black hole, was the only physically plausible mechanism. This was established theoretically by Donald Lynden Bell and others in the late 1960s and early 1970s. The discovery that galaxies harbor massive central black holes, even when not in an active quasar phase, came from careful observations of stellar motions in nearby galaxy centers. If a massive dark object sits at the center of a galaxy, the stars nearest to it orbit at speeds reflecting that mass. By measuring stellar velocities near galactic centers, astronomers could infer the presence and mass of central black holes, even when they were not actively accreting. This work culminated in observations of the Milky Way's own center, showing stars in tight, rapid orbits around an invisible object with the inferred mass of roughly 4 million solar masses. That object is Sagittarius A star, the first direct image of a black hole, or more precisely, the first image of the shadow of a black hole against the glow of its accretion disk, was produced in 2019 by the Event Horizon Telescope collaboration. The image showed the black hole at the center of the galaxy Messier 87, which has a mass of approximately 6.5 billion solar masses, roughly a tenth the mass of TON 618. The image matched theoretical predictions with extraordinary precision and was widely recognized as one of the great observational achievements in the history of astronomy. 2 years later, in 2022, the same collaboration published an image of Sagittarius A star, the black hole at the center of our own Milky Way. Despite being enormously closer than the Messier 87 black hole, Sagittarius A star presented a more challenging target because its smaller mass means it varies on shorter timescales, and the image had to be constructed from observations taken over multiple nights. Both images confirmed the basic geometric predictions of general relativity. The shadow of the black hole, the dark central region, had the size and shape predicted by Einstein's equations. The bright ring surrounding it was the emission from gas being heated as it spiraled into the event horizon. The universe, at least in these cases, was doing exactly what Einstein said it should do. TON 618 is too distant for anything like direct imaging with current technology. The angular size of its event horizon on the sky is far too small for even the Event Horizon Telescope, which combines signals from radio observatories across the entire diameter of the Earth, to resolve. What we know of TON 618 comes from the integrated light of the quasar, analyzed spectroscopically, with the black hole mass inferred from the dynamics of the gas surrounding it. The reverberation mapping technique that provides the most reliable mass estimate for distant quasars is based on a simple but powerful physical principle. Gas clouds surrounding the central black hole respond to changes in the brightness of the central source. When the quasar brightens, those gas clouds eventually brighten in response. The time delay between the central brightening and the response of the surrounding gas tells you how far the gas is from the center, because the delay is simply the light travel time between the two regions. Combine the distance of the gas from the center with the velocity of that gas, measured from the Doppler broadening of emission lines in the spectrum, and you can calculate the mass of the central object via straightforward orbital mechanics. This technique has been applied to hundreds of active galactic nuclei, and its results have been cross-calibrated against other mass estimation methods. For the most luminous and distant quasars, where direct monitoring of light curve variations is challenging, the masses are sometimes estimated from single-epoch spectra, using empirical relations calibrated on objects where reverberation mapping has been carried out directly. The uncertainties are larger in these cases, but the fundamental physics is sound. The specific emission line most commonly used for mass estimates of high-luminosity quasars is the broad emission of hydrogen known as the Lyman alpha line, or for somewhat lower redshift objects, the broad emission of carbon ions. These lines are produced by gas in what is called the broad line region, a population of clouds orbiting close to the central black hole at velocities typically measured in thousands of kilometers per second. The width of these emission lines is directly related to the orbital velocity of the gas, which in turn reflects the mass of the black hole they are orbiting. For TON 618, multiple independent analyses using different emission lines and different calibrations have consistently returned mass estimates in the tens of billions of solar masses. The lower estimates, around 40 billion solar masses, and the higher estimates, around 66 billion solar masses, arise from differences in calibration assumptions and the choice of emission line used. All of them are extraordinary. One fascinating aspect of studying TON 618 and similar extreme objects is what they tell us about the conditions required to feed a black hole at this rate. An accretion disk around a supermassive black hole is not a simple object. It is a turbulent, magnetized, radiation-dominated structure where gas spirals inward under gravity, while angular momentum is transported outward by magnetic and viscous stresses. The physics of this disk determines how fast material falls in, how efficiently gravitational energy is converted to radiation, and how the disk responds to changes in the accretion rate. The magnetic fields threading the disk and the corona above it are believed to be responsible for the collimated relativistic jets that some active galactic nuclei produce. These jets, which stream outward along the rotation axis of the black hole at velocities close to the speed of light, are among the most energetic sustained phenomena in the universe. The jet production mechanism involves the extraction of rotational energy from the spinning black hole itself through a process called the Blandford-Znaic mechanism, proposed by two British physicists in 1977. A black hole can spin. In fact, any black hole formed from the collapse of rotating material, or that has been spun up by the angular momentum of accreting gas, carries angular momentum. A rotating black hole is described by the Kerr solution to Einstein's field equations, derived in 1963 by the New Zealand mathematician Roy Kerr. The Kerr black hole has two parameters: its mass and its spin. The spin is bounded between 0 for a non-rotating black hole and a maximum value corresponding to what is called a maximally spinning or extremal Kerr black hole. The spin of a black hole affects its structure in important ways. A rapidly spinning black hole drags space-time around with it in a phenomenon called frame dragging, which causes the innermost stable circular orbit to be closer to the event horizon than in the non-rotating case. This in turn affects how efficiently gravitational energy is released as infalling matter spirals in. A maximally spinning black hole can convert up to 42% of the rest mass energy of infalling material into radiation, compared to only about 6% for a non-rotating black hole. This difference is enormous and has implications for the luminosity of quasars. The spin state of TON 618 is not directly measured. Its luminosity and other properties are consistent with a rapidly spinning black hole, but the uncertainties in the models make definitive conclusions impossible. Measuring the spins of supermassive black holes is one of the frontiers of observational astrophysics, requiring very high-quality X-ray spectral observations that can probe the innermost regions of the accretion disk. The broader context of TON 618 and the population of known ultramassive black holes is also worth understanding. A handful of objects in this extreme mass range have been confirmed. Home 15, A star, a giant elliptical galaxy in the Abell 85 galaxy cluster, harbors a black hole estimated at around 40 billion solar masses. Phoenix A in the Phoenix Galaxy Cluster may harbor a black hole of comparable or possibly larger mass, though mass estimates for the most extreme objects carry significant uncertainty. TON 618, at its estimated mass, sits at or near the top of this population. The host galaxies of the largest known black holes tend to be giant elliptical galaxies, the largest and most massive galaxies known. These elliptical giants are believed to have assembled through mergers of smaller galaxies over cosmic history. Each galaxy merger would have brought together the central black holes of the merging galaxies, which then form a bound pair and eventually merge themselves through the emission of gravitational waves. This is the process by which ultramassive black holes are believed to have assembled over time from smaller supermassive progenitors. The timescale for two supermassive black holes at the center of a merged galaxy to come close enough together to emit gravitational waves efficiently and merge is one of the open questions in gravitational wave astrophysics. There is a theoretical puzzle called the final parsec problem, which points out that simple dynamical friction, the gravitational interaction of the black hole binary with surrounding stars and gas, can bring the pair close together, but may stall at a separation of about 1 parsec, roughly 3¼ light years, before gravitational wave emission becomes efficient enough to drive the final inspiral and merger. Various mechanisms have been proposed to overcome this stall, including interaction with a triaxial stellar distribution, the influence of gas-rich environments, or the presence of a third black hole perturbing the binary. Observational evidence is beginning to accumulate for supermassive black hole binaries at various separations, though no confirmed merger has been directly observed. The Pulsar timing array experiments, which are large collaborations using networks of millisecond pulsars as extremely precise clocks distributed across the galaxy, have recently detected what appears to be a background of gravitational waves consistent with being produced by a population of supermassive black hole binaries throughout the universe. This detection, reported in 2023 by multiple independent pulsar timing array collaborations, is the first observational evidence for this gravitational wave background and provides indirect confirmation that supermassive black hole mergers are occurring throughout the observable universe. The gravitational waves from the merger of two objects with the masses of TON 618 would be among the most energetic events in the universe, releasing energy equivalent to a significant fraction of the total rest mass energy of the two merging black holes. These gravitational waves would have wavelengths of astronomical units and frequencies far below what any current or near-future Earth-based gravitational wave detector is sensitive to. The proposed space-based gravitational wave observatory known as LISA, the Laser Interferometer Space Antenna, is designed to be sensitive to exactly this frequency range and would potentially detect the gravitational waves from supermassive black hole mergers in the early universe if it is built and launched as planned. LISA, if approved and constructed on its current timeline, would open a completely new observational window on the most massive black holes in the universe, including objects like TON 618 or its local equivalents. Where current electromagnetic observations give us snapshots of the matter surrounding these black holes, gravitational wave observations would probe the black holes themselves, their masses, spins, and dynamics, in ways that are completely independent of the accreting material and its complex physics. The potential complementarity between electromagnetic and gravitational wave observations of supermassive black holes is one of the exciting scientific frontiers of the next few decades. If the universe is indeed full of massive black hole binaries awaiting merger, their gravitational wave signals are already present in our galaxy, already washing through the Earth, already slightly stretching and compressing the distances between the pulsars that the pulsar timing arrays are monitoring. We have just begun to learn to read those signals. Consider for a moment the full arc of what the study of TON 618 represents in the history of astronomy. A faint blue dot on a photographic plate in 1957, unnoticed for 15 years, eventually revealed to be the most massive confirmed black hole in the observable universe. A ghost of something that existed 10.5 billion years ago, showing us by its very existence that the rules we wrote for how the universe builds its largest structures are incomplete. The history of astronomy is full of cases where an object that seemed to be one thing turned out to be something far stranger. The faint nebulae that filled the catalogs of early observers turned out to be entire galaxies, each containing hundreds of billions of stars, scattered across a universe far larger than anyone had imagined. The faint radio sources and optical point sources of the 1960s turned out to be quasars, powered by accretion onto supermassive black holes, outshining entire galaxies from distances that make the size of the Milky Way seem irrelevant. TON 618 fits this tradition of unexpected revelation. And it is a tradition that continues. Every time astronomers build a new instrument more powerful than what came before, they find something that surprises them. The Hubble Space Telescope found that the expansion of the universe was accelerating, driven by what we call dark energy, but do not understand. The Event Horizon Telescope produced direct images of black hole shadows, confirming the predictions of general relativity. The James Webb Space Telescope is finding galaxies and black holes that are more massive, brighter, and more structurally mature at earlier cosmic times than any model predicted. We are in a period of genuine discovery. The standard model of cosmology, which describes the composition of the universe and the history of its structure formation with considerable success, is being challenged by a growing number of observations that do not quite fit. Whether those challenges require minor modifications to existing models or represent deeper foundational problems is being actively debated among the leading researchers in the field. TON 618 is not going away as a problem. Its mass is measured. Its redshift is measured. The chronological challenge it poses is real. The answer will come from better theory, better observations, or both. And when it comes, it will almost certainly reveal something about the early universe that we did not previously know. The object itself is not threatening. It will not affect our solar system. Its light, arriving nightly at our telescopes, carries no harmful energy. But it carries something perhaps more interesting than physical danger. It carries evidence that the universe is stranger, larger, and more capable of extremes than we have managed to account for. That is, in the end, why TON 618 matters. Not because of what it will do to us, but because of what it tells us about where we are. We live in a universe that builds objects like this. We are creatures small enough that the event horizon of a single black hole in a distant galaxy is large enough to swallow dozens of our solar systems without noticing. We have existed for the equivalent of a fraction of a heartbeat in the lifetime of a universe that was already building monsters before our sun had formed. And in spite of all that, we have figured out, from this small rock, using light that has traveled longer than our solar system has existed, approximately how massive that distant monster is. We have worked out approximately when and how it formed. We have identified where our models of its formation break down. We are asking the right questions. The questions are hard. The answers are not yet in. But the investigation is ongoing, and it is one of the most consequential investigations in the history of human thought. What is the universe made of? How does it build its most extreme structures? What are the fundamental rules governing the behavior of matter and energy and space-time at the most extreme conditions they can reach? TON 618 is one piece of that enormous puzzle. It is a piece that does not yet fit neatly with the others. And that, in science, is where the most interesting work happens. The light arrives tonight. Ancient photons completing a journey of 10.5 billion years, entering the mirrors of telescopes on mountaintops, carrying their quiet message from a universe that no longer exists. The message is about scale and time, and the limits of what we thought we knew. We are still learning to read it. And the reading, with each new observation and each new theoretical advance, keeps revealing that there is more to learn than we imagined. To appreciate what makes TON 618 particularly striking as an object of study, it is worth stepping back and examining how the scale of the universe was itself gradually discovered, because the story of that discovery is, in many ways, the story of how human beings learn to place themselves within a cosmos whose true dimensions are almost incomprehensible. For most of human history, the universe that people could conceive of was small. The stars were lights in the sky, relatively nearby, arranged in fixed patterns. The idea that those points of light were themselves suns, potentially surrounded by their own worlds, was present in the philosophical speculations of ancient thinkers, but had no observational basis. The universe of common human intuition was a universe scaled to human experience. The expansion of that picture began in earnest in the early 20th century. The distance to the nearest stars was established through parallax measurements in the 19th century, which revealed that even the closest stars were trillions of kilometers away. But the full scale of the galaxy, and the existence of other galaxies beyond it, was not established until the 1920s. The key breakthrough came from the astronomer Edwin Hubble, working at the Mount Wilson Observatory in California with the then largest telescope in the world. Hubble identified individual pulsating stars called Cepheid variables in the faint nebulae that dotted the sky, objects like the Andromeda Nebula that had been catalogued but whose nature was disputed. Cepheid variables have a reliable relationship between their pulsation period and their intrinsic luminosity, which means that by measuring how fast they pulsate, you can determine how bright they actually are. Comparing their actual brightness to how bright they appear in the telescope, you can calculate how far away they are. What Hubble found was that the Cepheid variables in Andromeda were at a distance of roughly 900,000 light-years, far beyond the boundaries of the Milky Way. Modern measurements place Andromeda at about 2.5 million light-years. Either way, it was unmistakably another galaxy, comparable in size and structure to our own. The universe was not the Milky Way. The Milky Way was one galaxy among many. Hubble went on to discover the relationship that bears his name. More distant galaxies have their light shifted more strongly toward the red end of the spectrum, and the amount of redshift is proportional to distance. The universe is expanding. Every galaxy is moving away from every other galaxy as the space between them grows. This discovery transformed cosmology. It implied that the universe had a finite age, that it had begun in an extremely hot, extremely dense state, and that it had been expanding ever since. The Big Bang Theory, confirmed by the discovery of the cosmic microwave background radiation in 1965, gives us the framework within which TON 618 must be understood. The universe is approximately 13.8 billion years old. It began as an extraordinarily dense, hot state and has been expanding and cooling ever since. Structure, meaning galaxies and clusters of galaxies, formed as gravity slowly amplified tiny density variations present in the early universe into progressively larger and more massive objects over billions of years. The problem with TON 618 is that it does not fit comfortably into this timeline. In the standard model of structure formation, based on the behavior of the dominant form of matter in the universe, which we call cold dark matter, the growth of structure proceeds hierarchically. Small objects form first. Larger objects form later by merging smaller ones. Supermassive black holes are expected to grow slowly from small seeds over cosmic time. TON 618 says otherwise. It says that the universe had already assembled an object of extraordinary mass within the first few billion years of its existence, long before the standard model predicts such objects should have been possible. The issue is not merely theoretical. It connects to one of the deepest unresolved problems in physics, the nature of dark matter itself. Dark matter is the dominant form of matter in the universe. It does not emit, absorb, or reflect electromagnetic radiation. It is invisible in every waveband. But its gravitational influence on the visible matter in galaxies and galaxy clusters is unmistakable. Without dark matter, the rotation curves of galaxies would not match what we observe. The formation of large-scale structure in the universe would not match the distribution of galaxies we see. The cosmic microwave background would not have the pattern of temperature variations we measure. The cold dark matter model, which describes dark matter as made of slow-moving particles that interact only through gravity and possibly a weak nuclear force, has been remarkably successful at explaining the large-scale structure of the universe. But it is not perfect. On small scales, the predictions of the cold dark matter model for the number and internal structure of small galaxies are in tension with observations in ways that are still being debated. Whether the growth problem for supermassive black holes in the early universe is connected to these small-scale tensions is unclear. It is possible that some aspect of dark matter's nature that is not captured by the simplest cold dark matter models affects the rate of structure formation in the early universe. Some alternatives to cold dark matter, including warm dark matter and fuzzy dark matter, predict somewhat different early universe structure formation histories that might alleviate some of the growth problem. But these alternatives introduce their own tensions elsewhere. The honest position is that we do not know what dark matter is. We know it exists because of its gravitational effects. We have been searching for dark matter particles in underground detectors, at particle accelerators, and through astrophysical observations for decades without a confirmed detection. The nature of dark matter remains one of the central unsolved problems in physics, and its solution may have implications for the growth of structures like TON 618. There is another deep connection worth exploring. The formation of large black holes in the early universe is linked to the formation of the first stars and the first galaxies, which in turn depends on the detailed physics of how primordial gas cools, fragments, and collapses into gravitating objects. The very first stars formed from gas that was almost entirely hydrogen and helium, with trace amounts of lithium and a handful of other light elements produced in the Big Bang nucleosynthesis during the first few minutes of the universe's existence. There were no heavy elements. No carbon, no oxygen, no silicon, no iron, none of the elements that make up the rocks and oceans and living things on Earth today. Those elements were forged inside stars and dispersed when those stars died. The absence of heavy elements in the first stars changed their physics in important ways. Heavy elements, called metals by astronomers in a terminology that differs from everyday use, are efficient coolants. They radiate energy effectively, allowing gas clouds to cool and fragment into smaller pieces as they collapse. Without metals, the gas clouds in the primordial universe cooled less efficiently, which means they had to collapse to higher densities before fragmentation occurred. The stars that formed from these more slowly cooling clouds were likely to be more massive than typical stars today. Theoretical models suggest that the first stars may have had masses of hundreds to thousands of times the mass of our Sun. These hypothetical massive first stars are called population 3 stars, the third and oldest stellar population in the astronomical classification scheme. Population. 2 stars are the older metal-poor stars found in the ancient globular clusters and halo of the Milky Way. Population 1 stars are the younger metal-rich stars, like our Sun. Population. 3 stars predate all of them. Population. 3 stars, if they existed as theory predicts, would have lived extremely briefly. A star 100 times the mass of our Sun exhausts its hydrogen fuel in only about 3 million years, compared to about 10 billion years for a star like the Sun. A star of 1,000 solar masses might have a lifetime of only a few 100,000 years. These stars burned hot and bright and fast, and when they died, they left behind black holes with masses potentially ranging from tens to hundreds or even thousands of solar masses. These massive remnants from the first stellar generation could then have served as seeds for rapid black hole growth in the early universe, accreting from the abundant surrounding gas and merging with each other in the dense early galactic environments. Whether this process can explain TON 618 depends on the details, and the details are uncertain because population 3 stars have not yet been directly observed. The James Webb Space Telescope has searched for signatures of population 3 stars in the most distant galaxies observable. Some candidate detections have been reported, based on unusual spectral signatures that could indicate the presence of extremely metal-poor, massive stars, but the evidence remains indirect and contested. Confirming the existence and properties of population 3 stars would be a major advance in our understanding of early cosmic history and would provide crucial information for models of early black hole growth. Another approach to understanding the growth of early supermassive black holes is computational. Astrophysicists use large-scale computer simulations to model the formation and evolution of galaxies and their central black holes from the earliest cosmic times to the present. These simulations, which have grown enormously in sophistication and computational scale over the past 2 decades, try to capture the relevant physics, including gravity, hydrodynamics, star formation, stellar evolution and feedback, and black hole accretion and feedback. The challenge is that the relevant physics spans an enormous range of scales. The overall large-scale structure of the universe requires modeling volumes of hundreds of millions of light-years. Individual black hole accretion occurs on scales smaller than the solar system. No simulation can simultaneously resolve both of these scales. Instead, simulations use approximations, called subgrid models, to represent the small-scale physics in terms that can be incorporated into the large-scale simulation. Different simulation codes, developed by different research groups with different choices of subgrid models, produce somewhat different results. This is expected, because the subgrid models are genuinely uncertain and the results are sensitive to those uncertainties. Comparing the predictions of different simulations with each other and with observations is a major part of the work of numerical cosmology. In recent years, several large-scale simulation projects have specifically attempted to reproduce the observed population of high-redshift supermassive black holes, including objects as massive as TON 618. To match the observations, these simulations often find that they need to include mechanisms for rapid early black hole growth that are not guaranteed by standard physics. Super Eddington accretion, large initial seed masses, or unusually efficient merging all appear in various simulation frameworks as ways to get the growth rates required. The fact that simulations need these mechanisms is itself informative. It tells us that whatever is happening in the real universe to produce TON 618, the standard picture of steady, Eddington-limited accretion from stellar mass seeds, cannot be the whole story. One of the more intriguing recent ideas comes from connecting the black hole growth problem to another long-standing puzzle in cosmology: the origin and nature of the magnetic fields that permeate galaxies and galaxy clusters. These fields are observed to be coherent over enormous scales, aligned across the entire extent of galaxies and even spanning the regions between galaxies and clusters. Where did these large-scale magnetic fields come from? In the very early universe, before structure formed, any magnetic fields present would have been extremely weak and small-scale. Theoretical arguments suggest that primordial magnetic fields, if they existed at all, would have been far too weak to explain the ordered fields we observe today. The fields must have been amplified and ordered by subsequent astrophysical processes. One mechanism for field amplification is the magnetorotational instability in accretion disks around black holes, which rapidly amplifies seed magnetic fields to the observed strengths in the disk. Jet production by spinning black holes then ejects this magnetized material into the surrounding galaxy and intergalactic medium, potentially contributing to the large-scale magnetic fields observed. In this picture, the activity of supermassive black holes, including objects like TON 618 during their quasar phases, played a role in magnetizing the universe. This is speculative, but it illustrates how the physics of supermassive black holes is deeply interconnected with the broader history and structure of the cosmos. These objects are not isolated curiosities. They are central actors in the story of how the universe evolved from a smooth, hot, homogeneous plasma to the rich, structured, complex environment we observe today. The interplay between supermassive black holes and their host galaxies, the process of active galactic nucleus feedback, is now recognized as one of the most important drivers of galaxy evolution. Without the heating and disruption of star-forming gas by quasar activity, many galaxies would have continued forming stars until they ran out of gas. Instead, quasar feedback at key moments suppressed star formation and led to the bimodal distribution of galaxy colors we observe today: a population of red, old, dead elliptical galaxies, and a population of blue, young, star-forming spiral galaxies. TON 618, during its active quasar phase, was doing this to its host galaxy. The enormous energy output from the accretion disk and jets was heating and dispersing the gas in the surrounding galaxy, suppressing star formation and shaping the galaxy's evolution. The light reaching our telescopes tonight is a snapshot of that process in action. What makes the study of TON 618 and similar objects so intellectually rich is precisely this interconnection. Understanding a single extreme object requires understanding stellar evolution, gas dynamics, gravitational wave emission, dark matter, cosmic structure formation, quantum field theory near black holes, and the history of the entire observable universe. It is a problem that touches every corner of physics and astronomy. The science being done on these questions is not esoteric. The instruments built to study them, the telescopes, the gravitational wave detectors, the space observatories, produce results that have rippled through physics more broadly. Techniques developed for analyzing faint signals from distant quasars have applications in signal processing and data science. The precision timing techniques used in pulsar timing arrays have implications for atomic clock technology. The computational methods developed for simulating galaxy formation influence how large-scale simulations are done in other scientific and engineering fields. And the questions themselves: what is dark matter? How does matter behave in the most extreme gravitational fields? What happened in the first fractions of a second after the Big Bang? Are among the deepest questions in all of science. TON 618 is a thread connected to all of them. Every few months, new papers appear in the scientific literature that are relevant to understanding objects like TON 618, new mass estimates based on improved observations, new theoretical models that propose better explanations for rapid early growth. new simulations that attempt to reproduce the observed quasar population, new Webb observations of high redshift galaxies and black holes that add more data to an already challenging picture. The pace of discovery is genuinely rapid. The community of researchers working on these questions is large and active. The debates are real and productive. The disagreements are about physics, not about whether the objects are interesting. For a viewer following this story, the most important thing to understand is that the uncertainty is not a failure. It is a sign of where the frontier of human knowledge currently sits. Science does not advance by confirming what is already known. It advances by taking the observations that do not fit, the objects that should not exist by current rules, seriously, and working out what they are trying to tell us. TON 618 is telling us something. The full content of that message is not yet clear, but the conversation between the object and the researchers studying it has been going on for more than half a century, and each decade it reveals something new. The photons are still arriving. The telescopes are still watching. The calculations are still being refined. And somewhere in the data already collected, in the archives of observations that have not yet been fully analyzed, in the patterns of light that have been crossing the universe since before the sun existed, the answer may already be waiting to be found. There is one more dimension of TON 618 worth exploring carefully, and it involves time in a way that goes beyond the simple statement that the light is old. When we say that the light from TON 618 is 10.5 billion years old, what we really mean is that the photons reaching our detectors were emitted 10.5 billion years ago. But the universe has been expanding during all that time. The object that emitted those photons is not 10.5 billion light years away from us as measured on a current map of the universe. Due to the expansion of space, the current distance from Earth to where TON 618 now sits, its so-called comoving distance, is actually considerably larger, somewhere around 30 billion light years. This distinction between the look-back time, the age of the light, and the current distance is one of the conceptually trickier aspects of cosmological measurement. Space itself has been expanding during the journey of the photons, stretching the wavelengths of the light and increasing the distance between the emitter and the receiver. By the time the photons have completed their journey, the object that emitted them has been carried much farther away by the expansion of the universe than the simple travel time of the light would suggest. This means that TON 618 is, in the real present moment of the universe, approximately 30 billion light years away from Earth. The expansion of space is carrying it away from us at a rate that, at that distance, corresponds to a recession velocity several times the speed of light. Again, this is not a violation of special relativity, because it is space itself that is expanding, not the object moving through space. We will never be able to communicate with, visit, or in any direct way interact with TON 618. The causal boundary between us and it is absolute. Even if we sent a signal at the speed of light today, it would never reach TON 618 because the expansion of the universe will carry the destination away faster than the signal can approach it. In this sense, TON 618 exists for us only as information, only as photons carrying a record of something that happened in a part of the universe forever beyond our physical reach. The information is real, useful, and scientifically valuable, but it is information about a past state of an object whose present state we can never access. This has a certain philosophical resonance that is worth acknowledging without overplaying. A significant fraction of what we know about the universe is knowledge of things we can never directly interact with. We know the composition of the sun by analyzing the spectrum of its light, not by sending a probe into its core. We know the composition of distant galaxies by the same method. We know the history of the early universe from the pattern of the cosmic microwave background radiation, light that was emitted when the universe was only about 380,000 years old, now redshifted into the microwave range by 13.5 billion years of expansion. All of this knowledge, the knowledge that allows us to say with confidence that TON 618 has a mass of tens of billions of solar masses and existed when the universe was less than 4 billion years old, comes from interpreting radiation. Electromagnetic radiation of various wavelengths, carrying encoded information about the physical conditions of the objects and environments that emitted it. Our ability to extract that information depends on understanding the physics of radiation emission and absorption in extreme environments. It depends on the quantum mechanics of atomic transitions that produce the spectral lines we analyze. It depends on the general relativity that allows us to interpret the redshifting of those lines as a measure of distance and age. It depends on the nuclear physics that tells us what elements produce what spectral signatures. Every piece of that understanding has been tested and validated in Earth-based laboratories and in the study of nearby astronomical objects where comparison and cross-checking are possible. The confidence with which we apply these principles to distant objects like TON 618 is grounded in decades of careful calibration work. This is not an incidental point. In discussions of extreme astronomical objects, there is sometimes a temptation to treat the most distant measurements as inherently more speculative. But the physics being applied is not speculative. The application of known physics to new observational domains is exactly how science works, and the track record of that approach is excellent. When theoretical predictions based on known physics have been tested against observations of distant objects, from the gravitational lensing of background galaxies to the spectral properties of quasars, the agreement is generally excellent. The places where the agreement breaks down are precisely the places where the science is most interesting. The growth problem for early supermassive black holes is one of those places. The tension between observed early galaxy masses and theoretical predictions is another. The nature of dark energy, which drives the accelerating expansion of the universe, is another. These are not failures of the scientific method. They are the leading edge of the scientific method in action. It is worth considering how TON 618 would have looked had humanity developed the ability to observe it at different points in its history. If we had been able to study it in the first few billion years of the universe, when the object we observe was still active, we would have seen a quasar of extraordinary luminosity. The central accretion disk blazing across the electromagnetic spectrum, jets potentially extending for tens of thousands of light years into the surrounding intergalactic medium. A host galaxy turbulent with star formation, its gas heated and disrupted by the quasar's output. In that environment, ordinary stellar evolution would have been disrupted. The intense radiation from the quasar would have ionized and heated gas across enormous volumes of the surrounding galaxy, suppressing star formation in some regions while potentially triggering it in others through compression of gas clouds. The chemistry of the interstellar medium in the host galaxy would have been affected. The heavy elements produced by the first generations of stars and redistributed by supernovae and stellar winds would have been mixed through the galaxy by the turbulent motions driven by quasar feedback. The host galaxy of TON 618, at the epoch we observe it, was not a quiet, orderly structure like the Milky Way we inhabit today. It was a young, turbulent, actively evolving system in the midst of building itself, with a monster at its center that was simultaneously growing from the available fuel and disrupting the processes that fed it. 10.5 billion years later, in the actual present moment of the universe, that galaxy has had most of its life to settle down. The quasar phase presumably ended when the supply of cold infalling gas was exhausted or dispersed. The host galaxy's star formation rate declined. What was once one of the most luminous objects in the universe became dark and quiet, a large elliptical galaxy sitting in the dark, its central black hole no longer glowing, but still holding everything in its gravitational grip. Or perhaps not. We genuinely do not know the current state of the object. We cannot know. The information about its present state is still in transit, will not arrive for billions of years, and may never be received by any intelligence capable of understanding it. The universe's most extreme object sits in permanent observational shadow, visible to us only as it was, never as it is. There is also the question of what happens in the very deep future to objects like TON 618. On timescales of hundreds of billions of years, the Milky Way will have merged with Andromeda and eventually with other nearby galaxies in the local group. The combined system will eventually lose most of its stars through gravitational interactions and evaporation, with the remainder falling into the central black hole or being ejected into intergalactic space. The central black hole of the merged system, which will itself have grown through mergers, will ultimately sit alone in an increasingly empty cosmic environment. On timescales of trillions of years, the expansion of the universe will have carried all other galaxies beyond the observable horizon. An observer in the far future, in whatever remains of our galaxy, would see a universe that appeared to contain only our own island of stars, slowly dying, with everything else beyond the observable boundary. On even longer timescales, the stars themselves will have burned out. The white dwarfs that remain will slowly cool. The neutron stars and stellar mass black holes scattered through the galaxy will persist longer. The central supermassive black hole will remain, slowly accreting the occasional passing object, slowly growing dimmer as it runs out of fuel, slowly evaporating through Hawking radiation at a rate so slow as to be essentially unobservable on any timescale comprehensible to human thought. But on timescales measured in 10 to the 100th power years and beyond, even TON 618 will eventually complete its evaporation. What happens in the final stages of black hole evaporation is one of the deepest unsolved problems in physics. The information paradox, the question of whether information about the matter that fell into the black hole is preserved or destroyed, will not be resolved by observation of TON 618 or any other large black hole. It may be resolved by theoretical progress that reconciles quantum mechanics and general relativity into a unified theory of quantum gravity. The search for that theory, a quantum description of gravity and spacetime that reduces to general relativity in the appropriate limit and to quantum field theory in another, is one of the central enterprises of theoretical physics. String theory, loop quantum gravity, and various other approaches have been developed and refined over decades. None of them has yet produced predictions that can be definitively tested against observation. But the black hole information paradox and the behavior of matter in the extreme environments near black hole singularities are expected to be important touchstones for any successful theory of quantum gravity. The most extreme black holes, including objects like TON 618, are in this sense laboratories for physics that we cannot test any other way. Not because we can probe their interiors, which we cannot, but because their existence and properties constrain what theories of physics can plausibly describe. The study of extreme astronomical objects has historically been one of the most productive interactions between observation and fundamental theory. The existence of neutron stars, predicted theoretically in the 1930s, was confirmed observationally in the 1960s, when pulsars were discovered and recognized as rapidly rotating neutron stars. The existence of black holes, long considered speculative, was effectively confirmed by observations of binary X-ray sources in the 1970s and 80s, and confirmed definitively by gravitational wave detections and direct imaging in recent years. The existence of dark matter, inferred from galaxy rotation curves and cluster dynamics, has shaped the entire framework of modern cosmology. TON 618 contributes to this tradition by revealing a regime of black hole mass and formation timescale that our theories do not yet adequately describe. The object is observational evidence that something in our model of early cosmic evolution is incomplete. That incompleteness is not a comfortable position for the field to be in, but it is an honest one, and it is exactly the kind of situation that historically leads to genuine progress. The researchers working on these questions will not arrive at an answer quickly. These are hard problems requiring careful observation, sophisticated theory, and the willingness to take unexpected results seriously even when they challenge established frameworks. But the record of physics and astronomy over the past century is one of exactly this kind of progress. From relativity to quantum mechanics, to the discovery of the expanding universe, to the standard model of particle physics, to gravitational wave astronomy, TON 618 sits in the lineage of observations that forced scientific understanding to expand. It is in good company, and the work of understanding it is in good hands. The photons keep arriving, the investigation continues, and somewhere between what we know and what we do not yet know, the universe is waiting to reveal its next surprise. Let us also consider the full chain of physical reasoning that connects a point of faint blue light on a photographic plate from 1957 to the extraordinary conclusions we draw about TON 618 today. This chain is worth making explicit because it illustrates both the power and the limitations of astronomical inference. Step 1. A photographic survey in Mexico records a faint blue point of light and logs it as a stellar object. Nothing unusual. Thousands of similar entries on the same survey. Step 2. 15 years later, spectroscopic analysis reveals that the spectrum of light from this object does not match any known stellar spectrum. The emission lines are shifted so far toward longer wavelengths that they fall at positions characteristic of known atomic transitions, but observed at wavelengths far longer than those transitions normally produce. This shift is consistent with a very large redshift. Step 3. interpreting the redshift as a Doppler shift due to the expansion of the universe. Following the Hubble relation established in the 1920s and refined continuously since then, gives a distance of approximately 10.5 billion light-years and a look-back time of roughly 10.5 billion years. Step 4. From the distance and the observed brightness, combined with a correction for the absorption and scattering of light by dust and gas, both within the host galaxy and in the intergalactic medium, one derives the intrinsic luminosity of the object. For TON 618, this luminosity is approximately 140 trillion times the luminosity of our Sun. Step 5. The mechanism producing such luminosity from such a compact region, a point source essentially, must be accretion onto a supermassive black hole. No other physical process can produce such extreme luminosity from such a small volume. Accretion converts gravitational potential energy to radiation with an efficiency of up to several tens of %, far exceeding the efficiency of nuclear fusion, which powers stars. Step 6. From the width of specific emission lines in the spectrum, using the virial theorem and the reverberation mapping calibration, one estimates the mass of the central black hole. For TON 618, this mass is approximately 40 to 66 billion solar masses. Step 7. Checking this mass against the time available for black hole growth in the early universe, using the Eddington limit as the maximum physically plausible accretion rate for conventional physics, reveals that standard growth models cannot account for this mass in the available time. The object should not have been able to grow this large, this fast. Each step in this chain relies on established physics that has been tested and validated in multiple independent ways. The interpretation of spectral shifts is foundational to all of modern astronomy and has been confirmed in countless contexts. The Hubble relation is measured to high precision using multiple independent distance indicators. The luminosity to mass conversion for quasars is calibrated against objects where multiple independent mass measurements are available. The virial mass estimator has been validated through reverberation mapping of hundreds of nearby active galactic nuclei. The conclusion that TON 618 poses a real challenge to standard models of early black hole growth is not a result of any single uncertain measurement. It is a conclusion built on a chain of well-tested physical reasoning at every step. The only way to escape that conclusion is to argue that one or more of the steps in the chain is systematically wrong in a way that current calibrations have not revealed. Perhaps the Eddington limit can be exceeded more easily than we think. Perhaps the mass estimators used for very high luminosity quasars have a systematic bias. Perhaps the physical conditions in the early universe allowed accretion at rates that are impossible today. These are all possibilities that researchers actively consider and test, but the current evidence does not support any of them strongly enough to resolve the problem. The mass is high, the redshift is high, the growth timeline is tight. TON 618 is what it appears to be. One of the most productive things a student of astronomy can do when encountering claims about extreme objects is to ask, at each step, what is the evidence and how well tested is the method? In the case of TON 618, the answers at each step are reassuring. The evidence is real, diverse, and extensively cross-checked. The problem is not a measurement artifact. It is a real feature of the universe that our best theories do not fully account for. That is a productive and exciting place for a science to find itself, not paralyzed by uncertainty, but energized by a clear discrepancy between what the universe shows us and what our best models predict. The history of physics is largely a history of taking such discrepancies seriously and finding that they point toward deeper truths. The ultraviolet catastrophe in classical thermodynamics, the failure of 19th century physics to correctly predict the spectrum of light emitted by hot objects, pointed toward quantum mechanics. The anomalous precession of Mercury's orbit, a tiny deviation from the predictions of Newtonian gravity, pointed toward general relativity. The unexpected dimness of distant supernovae, discovered in the late 1990s, pointed toward the accelerating expansion of the universe, driven by dark energy. TON 618 is pointing at something. The direction is not yet fully clear. It may point toward exotic initial conditions in the early universe. It may point toward new physics of accretion. It may point toward modifications of our standard model of cosmology. It may point toward something that has not yet been proposed, but it is pointing, consistently and unmistakably, at a gap in our understanding that deserves to be taken seriously and worked on with the best tools available. The best tools are being deployed. Webb continues to observe. Pulsar timing arrays continue to accumulate data. Theoretical work on black hole growth mechanisms continues to generate new proposals. Large-scale simulations continue to be run and compared with observations. Ground-based telescopes on mountaintops in Chile and Hawaii continue to take spectra of quasars at the edge of the observable universe. And every piece of data helps. Every new mass measurement of a high redshift quasar, every detection of a supermassive black hole in a galaxy that is younger than it should be, every failed attempt by a simulation to reproduce the observed population without invoking exotic physics adds to the picture. The picture, as of today, is incomplete. The edges of the puzzle are clear. The central piece is still missing. But the puzzle is being worked on by a global community of researchers with the best instruments in the history of astronomy and the deepest theoretical tools ever developed. There is one final thing worth noting about the light from TON 618. Every photon that completes the 10.5 billion year journey from that object to a telescope on Earth passes through an enormous volume of space that is itself full of structure and history. It passes through voids, the enormous empty regions between galaxy filaments, which extend for hundreds of millions of light years. It passes near galaxy clusters, whose gravity subtly bends its path, an effect called gravitational lensing that can be used to map the distribution of dark matter. It interacts with the diffuse intergalactic medium, the tenuous gas that fills the space between galaxies, imprinting subtle absorption features on the quasar spectrum that tell us about the thermal history and chemical composition of that gas across cosmic time. The quasar itself, in other words, is a backlight illuminating the universe between itself and us. The spectrum of that backlight carries information not just about the quasar, but about everything the light has passed through on its journey. This technique, studying the absorption features imprinted on quasar light by intervening structures, is called quasar absorption line spectroscopy and is one of the most powerful tools available for studying the intergalactic medium and the evolution of cosmic structure over cosmic time. TON 618, as one of the brightest quasars known, has been used extensively as a background source for this kind of analysis. Its extraordinary luminosity means that even after traveling 10.5 billion light-years, enough photons arrive to produce high-quality spectra. The absorption line forest in TON 618 spectrum, produced by hydrogen gas clouds at various redshifts along the line of sight, is a rich data set that has been analyzed by multiple research groups. This is a beautiful illustration of how a single object can be simultaneously a puzzle in its own right and a tool for understanding something else entirely. The existence problem of TON 618 challenges our models of early black hole growth. The light from TON 618, as a background source, helps us understand the distribution and properties of matter throughout the observable universe. Science at the frontier is like this. The same observation, the same piece of data, often bears on multiple questions simultaneously. The universe does not organize its secrets according to our research categories. The challenges and the tools come bundled together. TON 618 was not discovered because anyone went looking for the universe's largest black hole. It was found by accident, in a survey aimed at something else entirely, and its true nature took 15 years to be recognized. The most important discoveries in astronomy have often been made this way. The cosmic microwave background was discovered accidentally by engineers testing a new radio antenna. The first pulsar was initially dismissed as possible interference or a human-made signal before its regular pulses were recognized as the signature of a rotating neutron star. The accelerating expansion of the universe was found while astronomers were trying to measure how quickly the expansion was slowing down. The universe has a way of surprising us. The surprises come from measurements, from data, from light arriving from places we barely knew to look. TON 618 arrived on a photographic plate in 1957 and waited patiently for someone to understand what it was. Now we understand, at least partially. The understanding is incomplete. The gaps in it are scientifically important, and somewhere in those gaps, the universe is waiting to reveal what it has been hiding. That is where science lives, at the edge of what is known, taking measurements of what is there, trying to understand what those measurements are saying. The photons from TON 618 have been making the trip for 10.5 billion years. The scientists studying them have been working for a fraction of a human lifetime. The work is not finished, but it has already shown us something profound. The universe is stranger, larger, older in its extremes, and more capable of building things we cannot yet explain than we knew. TON 618 is the hard evidence. The investigation of what it means continues. And if that kind of question matters to you, the next discovery is already on its way.